Elementary matrices. So we talked about elementary row operations to reduce a matrix or whatever we do with matrices. And now there's this idea of an elementary matrix. What this allows us to do is to take a look at an actual matrix as an operation. So we've been looking at matrices as entities, as if they were vectors or as if they were numbers. We add, subtract, we do algebra on them, things like that. Now we're actually going to look at matrices from one point of view as an operation, while simultaneously looking at it as if it was another in its own entity that we add, subtract, and multiply and divide. And so we're going to look at this. The steps, you know, we've been kind of just considering it as steps, right? These are steps that we take to reduce a matrix into row echelon form. But now we're going to look at it as if it was an actual matrix. So an elementary matrix is a matrix that can be obtained by performing an elementary row operation on the identity. So if we had, for example, if we had, let's just take one of these matrices that I have an example. So if I'm looking at this A matrix here for number 39, for example, and I want to get that bottom left-hand corner to be 0, I would go through a row operation. Your elementary row operation, where we say I'm going to take my row 1. I want it to change colors. Take my row 1. Multiply it by, well, I just keep it at that, and then add it to row 2 and replace row 2 with it. And so what I would have is the first one remains the same, and the second one goes to 0, and then this becomes negative 2. Oh, while we're at it, let's just take this and make it go to the identity matrix, right? So let's do one more step here where we would, what would we do to make this into a 1? Multiply the second row by negative 1/2 and replace the second row by it. Okay, so those are two elementary row operations that we should be familiar with, right? Now, what this is saying is that these two operations are really matrices in itself. It says an elementary matrix is a matrix that can be obtained by performing an elementary row operation on the identity matrix. So we're dealing with 2 by 2 matrices, so let's start with a 2 by 2 matrix. The 2 by 2 identity matrix. And maybe I don't want to draw an arrow that long. Let's just say do this row 1 plus row 2 replace row 2 business on the identity matrix. So I'll take row 1 and add it to row 2, and this is an example of an elementary matrix. And I start off with an elementary matrix, and I take 1/2 row 2, replace row 2, then this is going to be not coming from this matrix, but coming from the original identity matrix, 1, 0, 0, negative 1/2. So these two are examples of elementary matrices. Okay, by definition, that's what an elementary matrix is. Okay? Yes? No. The A is just a random matrix. So A is not an elementary matrix. The only elementary matrices I have in this page is these two. So these are the only elementary matrices. None of these other ones are elementary matrices. A is just a random matrix. These two are elementary matrices. Yeah? How does a span relate to the elementary matrix? I don't know if the span relates too much to this. But we'll see how the inverse is related. Dan first, yeah. Because I needed two steps to get to this point, right? So the question, if A, yeah, it has to be one elementary row operation. There's another question? Was there oh, that was the same question? Yeah. Yeah, so A is not an elementary matrix. A is just some random matrix. So is the idea of an elementary matrix okay? The definition, at least? We'll talk about why it's important in a minute. Well, that's the point in this, yeah. That's why we're learning elementary matrices. Okay, so Victor was saying you multiply the elementary matrix with the original matrix to do your transformations, and that's exactly what we're going to look at, and that's exactly what we're going to do. Okay? All right. Is it too dark? Is it okay? Too dark? Okay. It's better with dark. Okay. All right. So let's see what else I have in my notes here. Theorem. So for this, I'm going to use a Mathematica just so I can do things a little quicker instead of doing the multiplication by hand. And also Mathematica is a little bit more meticulous than I am. So we're pretty much guaranteed correct answers as long as I put in the correct input. Versus me trying to do the multiplication by hand, in which case you may or may not be guaranteed the correct input. But you could check it yourselves, of course. But I'm just going to use Mathematica. So E is an elementary matrix obtained by performing an elementary row operation. That is the definition of an elementary matrix. If the same elementary row operation is performed on an n by r matrix A, the result is the same as multiplying that matrix with that elementary row operation. Okay? So, I don't know, did that make sense? All right, let's see how this is actually going to look like. So I pulled out my Mathematica so I don't have to do this multiplication thing, and so we're going to take a look at a couple of matrices. That matrix A, whatever that A was, what was that A? 1, 0, negative 1, negative 2. So 1, 0, minus 1, minus 2. So that's my matrix A. And one of the elementary row operations that I created was 1, 0, 1, 1. That is the same thing as adding row 1 to row 2 and replacing row 2, right? So 1, 0, 1, 1. That's one elementary matrix that I have. 1, 0, 1, 1. And then, just for good measure, let me write down the second elementary row operation that I had, which is 1, 0, 0, minus 1 half. Okay, so these are three of my matrices. Now, if you remember this row operation, we wrote it in the symbols that we've been using all semester, which may or may be different from the way you do it or where you might have seen it before. But I use R1 plus R2, arrow R2. Right? That says I'm going to take my row 1, add it to row 2, and replace row 2 with it. And this is the result. Well, if I do the multiplication of my E1 matrix, which is that operation itself, times A, the A matrix, I should get the same result. So let's see it come out. So I'm going to take E1 times A. Now the result here is going to look like a list, so I'll run it and then I'll redo it again. But just to make it to have you see it a little bit better in Mathematica, I can write it in matrix form so that it looks like, you know, a matrix. So this is the result, and this is exactly what we had before, right? Oh, that's cool. So let me type out A in matrix form and type out E1 in matrix form, just so we can see all of them. Whoops. Oh, sorry, I'm fiddling with this stuff. Just making the notes look nice. So, if we take our matrix A, multiply it with this elementary matrix that we found from last time, it's backwards. I need this elementary row operation first, and then the matrix A. Whoops. Sorry. So, matrix A, and then you multiply it by an elementary row operation on the left, and that should give you the result that we got last time. Okay? All right. So I'm going to now call this E1 because I'm going to take a look at this and say, hey, there's a negative 2 there. What if we want to get rid of that? Well, there's another elementary row operation I can apply on this. Right? That's E2. And that's to multiply the second row by negative 1/2. So if I do that, this is my result. If I multiply E2 by the result that I got from E1 times A, then I should get the identity matrix, because that's what I got last time. And what was E2 again? (1, 0, 0, negative a half). So notice that what I did was I multiplied not the original A, but the result that I got from the first multiplication. So I didn't multiply just A, right? I multiplied by E1 times A. So this is A, this is E1, and then I multiplied by E2. And then this gave me the identity matrix. Okay? So that turned out to be an interesting little fact and a little tidbit about these matrices and about finding inverses, because last time we were talking about finding inverses. And remember, the definition of an inverse is that if you multiply two numbers and you get the identity, then one of them must be the inverse of the other one. Remember? So recall the definition of inverse. Definition of inverse is that if you multiply a matrix by its inverse, you should get the identity matrix. Oh, here we go. We're getting the identity matrix. What does that mean? That means this is our A. Let me rewrite this. E2, E1, A. It's associative, so it doesn't matter where my parentheses goes. I can put my parentheses around E1 and A, like I did up there, or I can put my parentheses around E2 and E1. Should still be the same. And this is supposed to be equal to the identity. What does that mean? That means A times this thing must be the inverse of A. Right? So star E1 or E2 times E1 must equal to A inverse. Wow. This is wow. We got ourselves the inverse. Right? Let's double check that. Using Mathematica, of course. So if I just take E2, was it E1, E2, or E2, E1? Because that makes a difference. E2, E1. E2 times E1. E2 times E1. There it goes. Is this? This is the inverse, supposedly. Well, we know how to find inverse of 2 by 2 matrices, right? Do you remember? Of course we do. We just did it last week. Oh, but last week was a long time ago. What's 1 over the determinant times switch the diagonals, negative the wings for a 2 by 2 matrix. So this is supposedly your inverse. Let's check the inverse of A. What was A again? A is 1, 0, minus 1, negative 2. So A inverse, according to what we learned last week, was 1 over the determinant. Determinant is 1 times negative 2. That's negative 2 minus 0. So that's the determinant. Times, we switch the diagonals, so I'm going to switch the negative 2 and the 1. And then I'm going to take the wings and put negative in front of them. That 0 is already 0, but negative of negative 1 is positive 1. So we switch the diagonals and negative the wings. And if we carry out this scalar multiplication, we have negative 1/2 times negative 2. Negative 1/2, negative 1/2. So that's exactly what we got using our elementary row operations. So that's pretty cool. We could find our inverse just by looking at the elementary row operations. Okay? Nick?
There's a method for finding the inverse where you take 0 equals to A minus 1 over X. Can we do that with matrices?
0 equals A minus 1 over X.
And then when X is equal to, when that's true, it's not an inverse.
Well, I don't know if that works.
It's
'Cause
Newton's iteration.
okay, so X is X a matrix? Because we can't divide.
That's what I'm wondering.
Yeah, we can't divide by matrices, so I don't think that'll fly. There is another way to find inverses, which is to augment it with the identity matrix. I don't know if you guys were watching the video that was on before class started today, but another way to find inverse is to write your matrix. What's the matrix again? It's 1, 0, negative 1, 2, or negative 2? Negative 2. Is to augment the identity matrix on the other side and then do row operations to get this part of the matrix into the identity matrix, and then whatever result you get here is going to be your inverse. That's the more common way of finding inverses, and that's what people normally do. Okay? So I encourage you to try to do that here. This one takes a couple of row operations. If you have a 3 by 3 matrix, then that might be a little bit more work. But remember that this is you want this to be not just row reduced, not just row echelon form, but actually reduced row echelon form where you got zeros everywhere else. And it does have to be the identity matrix on this side. Okay. All right, so you guys can figure that out. Okay. So that's the elementary matrices, and that's why they're important. A couple more theorems to bring up. It turns out that each elementary matrix is invertible. It has an inverse, and its inverse is also an elementary matrix. I don't know if that makes sense, but let's take a look at the elementary matrix that we called E1 from before, where we take the first row, add it to the second row, and replace the second row with that. Let's see if we can find its inverse. Just for practice, let's do it the way we did or let's do it the way where I didn't show you, where you augment it with identity and then see what happens. So let's find the inverse of this. You start off with that original matrix, and then you have the identity on the other augmented part. And then we want the left-hand side of the matrix to be the identity, so I need to get rid of this. So what do I need to do to row 2? I need row 1 multiplied by -1, add it to row 2, and replace row 2. So that would give me the identity matrix on the left-hand side, right? So let's do this on this side. I take row 1, and then I multiply row 1 by -1 and add it to row 2. That's going to give me this. So the inverse of E1 should be this particular row operation. Let's check. E1 times E1 inverse is equal to 1, 0, 1, 1 times 0, let's say 1, 0, -1, 1. All right, I'm going to do this by hand. This is 1. This is 1, 0, 0. So that's 0. The row and the column. This is 1 minus 1 is 0. And okay, so it is in fact identity. And technically, you should check the commutative portion of this. So you switch the order, because multiplication is not commutative. You're not guaranteed that you're going to get the same answer. But let me just tell you that it'll work. So it is in fact the inverse. Without actually doing it, can you guys take a stab at what this inverse might be? Just by inspection. Okay, what is it? -1/4? What? 1/2? Oh, well, so what's the determinant? The determinant is -1/2. So 1 over -1/2 is -2. And we switch the order. So switch the diagonals, negative the wings are 0. So let's just switch the diagonals. This is -2 times negative a half. So it'll be 1. And then this becomes 1 multiplied by negative 2. Right? So do this in your head or whatever, but if you do this multiplication, you should get the identity matrix. So the inverse of this row operation, the first one, where we multiplied a row, added to another row, looks like it's going to be the same type of operation, except instead of multiplying by a 1, you multiply by a negative 1. And over here, it looks like it's the same sort of operation where you would multiply the second row by something, except you're going to multiply it by its reciprocal. Okay? So if you can remember that, and the way to try to remember this is to practice doing this. I mean, I could write it out, but what fun is that? You guys figure it out. So figure it out by practicing it and try to figure out the inverse of things. Now, there's another row operation that we didn't do in this example, isn't there? What's the other row operation that's legal that we didn't do? Switching two rows, right? Let's take a look at a switch of two rows. So one more operation. Switch rows. Where's the T go? Before the C? Switch rows. So let's call it E3. And if we take the identity, we're still stuck with sticking with a 2 by 2. If we take the identity and we switch the rows, is that right? Instead of 1, 0, 0, 1, it's 0, 1, 1, 0, right? And so, what do you think? What row operation do you think would get this back to the identity? What is the inverse of this? Switch the rows again. That's the same one. Isn't it? So you're telling me if I multiply these two things, I should get the identity. Is that what you're telling me? Yeah, row 1 and row 2 switched. E3 times E3 inverse, or what we're saying is E3 inverse. 0, 1, 1, 0. 0, 1, 1, 0. Column, row, row and column. How's that song go? Row times column. Row times column is 1. Row times column. This is 0, 0. Row times column, it's another 0. Row times column, it's 1. So yes. It's itself. The identity is itself. Man, that's only for 2 by 2 matrices. Let's check a 3 by 3 matrix. I'm just going to call it E4. Let's see, what do we want to switch? The first and second, the second and third? First and third, let's switch the first and third. So the first one and the third one, this is the first row, I'm going to move it down to the third. This is the third row, I'm going to move it down to the first, and so the middle row stays the same. I think we should switch the first and second. Can we switch the first and second row instead? No. Just going to erase. Switch first and second row. So first row, second row. This is the first row. This is the second row. So if I take a matrix, I switch the first and the second row, how do I get it back to its original state? Switch the first and second row again, right? So E4 inverse is the same thing as switching the first and second row again. And suppose we should check this. That'll work. You check it. Multiplied together, it should be the identity. So elementary row operations or elementary matrices have inverses, and their inverses are, well, if you just switch the rows, their inverses are itself. And then if you do the other two elementary row operations, one of them is an opposite. It's the same type of operation, except one of them is an opposite, and then one of them is a reciprocal. Okay? Again, practice this. You know, try out some matrices and multiply it by some elementary matrices and use Wolfram Alpha or use FreeMat so you can do these calculations quicker, but you'll see that there's that pattern going on. Okay? All right, so that's interesting. Elementary matrices have inverses. Now here is what they're calling the fundamental theorem of invertible matrices, version 1. So there must be version 2 later. Version 2 just adds more stuff to it. It's essentially the same thing, and then some more after we learn more about some of those other concepts. But we do know about invertibility in systems of linear equations, so we can at least go with a short list like this. Okay, so if A is an n by R matrix, the following statements are equivalent, which means if one of them is true, then all the rest should be true. So if A is invertible, then there must be a solution, a unique solution to your system of linear equations. There must be only the trivial solution if you're looking at the homogeneous system. The reduced row echelon form of A is exactly the identity. Or you'll see a piece of the identity there because this is not necessarily a square matrix. And A itself is a product of elementary row operations. What? A is a product of elementary row operations. What? Wait. A is a product of elementary row operations. Let's try to focus our thoughts on this last one. Using our simple example that we had A was equal to 1, 0, negative 1, negative 2. That's our 2 by 2 matrix that we were playing with earlier. Now we found that if we added the first row to the second row, and if we multiplied the second row, the result of that. We'll multiply the second row by, what is it, negative 1/2? Or, yeah, negative 1/2. Then we would get the identity, right? So we actually came up with this equation. And then I said something like, oh, it's associative, so I can regroup whatever I want on the left-hand side, blah, blah, blah. And then I said that this was the inverse of A. So if A has an inverse, that means I can get A by itself, right? And how would I get A by itself? Do you remember your algebra? Well, I can just quickly say, oh, I'm just going to multiply this on the left-hand side by E2, E1 inverse. Then I need to multiply this on the left-hand side by E2, E1 inverse, which means that's just the inverse. The I is anything times I is going to be whatever that is. So I just have E2, E1 inverse. So I should get this to cancel, right? Because they're inverses of each other, and so I get A is equal to, what's E2, E1 inverse? Is that E2 inverse, E1 inverse? E2, E1 inverse equals E2 inverse, E1 inverse. Is it? So that's, wait, that's what A is equal to? Oh yeah, A is a product of elementary matrices. And then inverses are elementary matrices, right? So is this good? Is this good? No. What did I do wrong? Nick? You can't apply the inverse to the parentheses. What do I have to do with the inverse to the parentheses like that? Okay, well that was good. At least you identified where the error was. What? Anybody else? This is not correct. So what is the correct thing to say here? Ming Ming? It's what? To undo the inverse, or to distribute the inverse through the parentheses, remember you have to switch the order. Matrix multiplication is not commutative. And so there's those funny properties for inverses of these things. And this is one of them. Take the inverse of a product, it's a product of the inverses, but in reverse order. Okay? So A, and remember that each elementary matrix has an inverse that's also an elementary matrix. And so A is essentially a product of these elementary matrices. And if you want to double check, just quickly use Mathematica. E1 we need to use brackets. So the inverse of E1 looks like this. The inverse of E2, we already figured those two out. The inverse of E2 is this. Remember, the E2 originally was a negative 1/2 here. So now it's, instead of negative 1/2, it's negative 2. Negative 2 over 1, the reciprocal. And then what we're interested in is finding the product of these inverses. So if I take the inverse of E1, multiply it with the inverse of E2, and look at the matrix form, we should get the original matrix A. This is the original matrix A, right? So it's all there. Okay? Pretty cool, huh? So what we're doing, let's see. I don't know what grade you were, but if back in the day, when you were first learning about numbers and multiplying and stuff like that, the teacher gave you 32, and they say factor 32. And then you made that tree. 32 is 8 times 4, and then 8 is 4 times 2, and then you did all that stuff, and you found that 32 is equal to 2 times 2 times 2 times 2 times 2 to the 5th power. Right? So think about elementary matrices as these prime numbers. And think about the product of these elementary matrices as the prime factorization of a matrix. That's essentially what we're doing. We're taking the matrix and we're breaking it down to simple numbers or simple matrices, which wouldn't call it prime, but elementary matrices, the simplest type of matrices that we can come up with. Okay.
Can you perform these row operations if you're trying to find the span of two matrices? Like two by two matrices, can you reduce them to this and then find the span?
I don't know how much a span plays into this, because if I'm looking at the span of a matrix, I need to come up with a different system of linear equations, and that would come up with a different matrix that looks different from the original matrices that we're dealing with. So I don't know how much the span will play into this.
So that would be a valid way?
Probably not. All right, so we got a couple of equivalences. So if we know that A is invertible, then we know that the product, A is a product of elementary matrices, and we know that it satisfies all this other stuff. Okay, let's see if we can come up with one more theorem here for this section, for this chapter, maybe a few more theorems. Okay, this one says that if you have a square matrix and B is a square matrix such that it's equal to that, then B must be the inverse. Yeah, I don't know. That doesn't sound too exciting. So let's move on to the next one. And this one says if A is a square matrix. Oh, this is the one where this is how most people find their inverses. If A is a square matrix, then a sequence of elementary row operations reduces A to the identity matrix. Then the same sequence of elementary row operations transforms I into A inverse. Okay? And what's nice about the elementary matrices is, I don't know if it's nice for you, but for a mathematician, they use elementary matrices as a way to prove these theorems. So, for example, if we know that A is a square matrix and A is invertible, then that means A, so let's do a little mini proof here. And that means A, if you multiply it by a bunch of elementary row operations, I don't know how many of them, so usually people just put dot, dot, dot. And let's say after k elementary row operations on this matrix, I'm going to eventually get the identity just like I did with those 2 steps to find that 2 by 2 matrix identity. And so what you're essentially doing is you're essentially making this A into this identity matrix, and then what you're doing also is you're making this identity into that row operation business. What? I don't know if I said that right. Let's just pretend I said it right. So A is equal to the inverse of these things. Remember the inverse? The inverse of this whole thing is the same as the inverse of each of them multiplied backwards. Oh no, that's not what I want. I wanted this. It's even more straightforward than this. This is not needed for the proof. Let's ignore this. But this is saying that EK times EK minus 1, etc. This thing works as the inverse of A. And what we can do is we can imagine that EK times all this stuff gets multiplied by the identity, which is to say what we're doing here is we start off with identity, and then you perform the first row operation, and then you perform the second row operation, and then you perform the last row operation. So there's all kinds of parentheses here. And you're performing it on I, and then that's how you're going to get the inverse. So you're performing your row operations on I. The same row operations that will give you the identity matrix for A is going to give you the inverse of A for that side. So this isn't a formal proof, but this is how you prove, this is how mathematicians would prove it, now that this idea of an elementary row operation can be described as a matrix. And the fact that it can be described as a matrix makes our proofs a little bit easier, or more mathematical. All right. Yeah, this isn't too formal, so I'm not going to put the QED business there. All right, let's see. Find the matrix. Ooh, over Z7, Z3. Well, let's do one of these Z ones. Let's do the 2 by 2 one. Over Z5. The other ones might take a while. Kind of keep us practicing, keep us fresh on working with finite fields here. Again, I asked you to try doing some of these other ones. You guys will have homework on it and stuff, but you should take one of these problems from the book or from somewhere, and then just find the inverse, and then go to Wolfram Alpha or MATLAB, and then ask to find the inverse and see if you get the right answer. Just so you can go through the process of finding inverses. So the example that we're going to do is is over a finite field Z5. So we're looking at this over Z5 just to give us some practice on finite fields again. And the way to start this off is to start this off looking like an augmented matrix, but the augmented part is the identity. All right, so this is Z5, so this is a lot. 0, 1, 2, 3, 4. Oh, you guys do circles? Does it matter? If it doesn't matter, if it's all the same to you, I'm going to do it like this. And then, so I know 5, 6. Oh, it's Z5, so I know how to multiply by 5s. And I guess I was concerned about the negatives. So if I go negative, -1, -2, -3, -4, -5, etc. So I can fill in top and bottom as I need to. All right, so the first question is, what do I need to multiply 4 by? So I think I would be interested in a row operation that takes 4 multiply the 4 so I get 1. Let's see. 4 times, I don't want to do 0. 4 times 1 is 4. 4 times 2 is 8, which is 3. 4 times, where am I? 1, 2. 4 times 3 is 12, which is 2. 4 times 4 is 16, which is 1. There it goes, 4. I want to multiply that by 4. So this is going to end up being 1, right? That's my main goal, to make that into a 1. And then I multiply 4 times 2. What's 4 times 2? 8? 8, and 8 is 3. So I multiply this by 4. Okay, I didn't do anything with this one, so I'll just leave it alone. So 3, 4, 0, 1. Next step, I'll take row 1, multiply that by something, and add it to row 3, or row 2, and then replace row 2. So 3 plus what will get 0? 3 plus 2 will get you 0, right? So if I multiply this by 2, this will be 2. 2 plus 3 is 5, which is 0, and that's what I want. All right? So the first row doesn't change. That's a 1, 3, 4, 0. And 2 times 1 is 2, plus 3 is 0. 2 times 3 is 6, plus 4 is 10. That's 0. Uh-oh. That's a bummer. And then let's finish this off. I'm in a little bit of a trouble here because now it's not the identity, so this is probably not invertible. So 2 times 4 is 8, which is 3. Add it to 0 is 3, and that's 0. All right, so one of the things that we should note is that this is not the identity, and we can't ever get the identity from here. So it looks like what was the matrix? 4, 4, 2, 3, 4, 4, 2, 3, 4 is not invertible. Over Z5. So we were not able to find the inverse over Z5, so kind of got stuck. Yeah.
So we can also do finding the determinant.
Yeah, but the determinant of this is trickier too because we're in Z5, so you know the determinant, you have fractions and stuff like that. That all needs to be translated to division, is multiplying by the reciprocal, which is a little bit more difficult for this. All right, so this has no inverse. Let's move on. That's a bummer. But I guess that's a good example. So this is what happens when you don't have an inverse, is that you're not going to be able to get your matrix into the identity. Okay, questions? All right, let's move on. So we're on to the next section, and this is called the LU factorization. And the LU factorization is another way to factor matrices. You know, we talked about the matrix. If it's invertible, then it's a product of these elementary row matrices. But now let's talk about factoring in general, or one way of factoring. It turns out that an upper triangular matrix, which has zeros in the lower part, lower left-hand part of the matrix, is a nice matrix to deal with. And turns out the lower triangular matrices are nice to deal with also. So if we can take a regular matrix and factor it into a product of upper and lower triangular matrices, then that might be cool to work with. So here are a couple of definitions. A square matrix is upper triangular if the entries below the main diagonal are zeros. So in other words, your upper triangular matrix, U, would have stars in the diagonals. Stars mean not necessarily zero, and more stars up here. And then zeros from below the diagonal on. A matrix is called unit lower triangular. Now there's a word unit that's included here that makes it a little trickier. And the definition for that means your lower triangular matrix is not just a regular lower triangular matrix, it's a unit lower triangular. What that means is that instead of just random elements in the diagonal, you actually have ones in the diagonal. And then below that can be anything, and above that are zeros. So what makes this a unit triangular matrix is that your diagonals are all ones. Okay? So if you have a square matrix, then, and if this factorization exists, sometimes it does, sometimes it doesn't. If factorization is an LU factorization, if you can write this as a product of L, some unit lower triangular matrix, times U, some upper triangular matrix, then you have the factorization of A. That is the definition of an LU factorization. Okay? So let's try it out. Do I have examples? I hope I have examples. Here's a matrix. A square matrix can be reduced in row echelon form without using row interchanges. That's one of the elementary matrix operations, right? You interchange the rows. So if we prohibit that, then we're guaranteed an LU factorization. So that means if we have to do a row switch, then we're not going to be able to do an LU factorization. That's a bummer. I hope we can find something else to do with those matrices. Anyways, let's see if we can come up with an example. I'm not going to make one up, just because it probably won't work. Should we brave a 4-byte? No. Oh, these are... I can't use these ones because they require a switch. The first component is 0, so they require a switch. So I can't do this one. Let's see if I can come up with another one. Let's see if I have your class up here. Wait, is it the next section? LU factorization? Now the answer is here, but let's just do this as an example anyways. So if we can row reduce this, wait, if we row reduce it, then that's the upper triangular matrix, right? Ah. Okay, well, let's row reduce this. Oh, man, I want to pick an easier one. All right, let's multiply the top one by 1/2. Oh, we're introducing fractions already. That's not a good sign. Wait, I don't need this to be ones. Never mind. Let's just multiply the row 1 by -3/2. And then add it to row 2 and replace row 2. So this would be 2 minus 8, 0. This is 0. So more algebra here. So this is positive 12 minus 7 is positive 5. And that's 0, so that's 8. Okay. Let me do another row operation here since we're here. Let's multiply this by a positive 1/2. Multiply the first row by positive 1/2 and add that to row 3. So that would make this 0. And this would be 0 again. Oh, nice. And then this would just be 2. Does that look good? All right. Well, look, this is already its row echelon form is upper triangular, right? This is already an upper triangular matrix. What does that mean? That means A is equal to this upper triangular matrix Well, it's not equal to that. Sorry, I'm not done with this equation yet. But we did a couple of row operations. There were elementary row operations at that, right? We did a couple of row operations that would make this into an upper triangular matrix. we did an E1 and an E2. See if we can identify those two matrices. What's your E2 matrix? The E2 matrix is taking row 1, multiplying it by 1/2, and adding it to row 3. What is that matrix E2 going to look like? Anybody? Anybody? Do you guys know what I'm asking? 1/2 R1 plus R3. That's my E2 matrix. So I want to write that. This is a 3 by 3 identity you're starting with, and then you're going to perform this operation on a 3 by 3 identity. What's it going to look like? 1/2, 0, 1. And everything else would be the same because I didn't change anything. Thank you. And then what's E1? E1 is -1/3 times row 1 added to row 2. The first and third doesn't change. 1, 0, 0, 0, 0, 1. The first and third rows don't change, but the middle one changes because I added 1/3, -1/3 times row 1 added to row 2. Three halves. I couldn't see without my glasses. I mean, with my glasses. I mean, without my glasses. I'm just telling my other class how I needed glasses. I mean, not glasses, but bifocals. You know, the progression lenses where, yeah, you guys are probably too young for that, huh? I'm refusing to get it because my doctor keeps telling me I should get it. And I said, no. All right. Well, you know that these things have inverses. And it turns out that the product of these inverses will end up being your L, the lower triangular. And we don't have time to show that, but I will show that to you next time. But that's how we're going to get your lower unit triangular matrix there. Okay? So, we're late. We're done. See you guys next time. I need to give you a quiz sometime. Wednesday? Tuesday? Let's have a quiz next time. I don't know what, though. What? Okay, I'll put in an announcement that there's going to be a quiz, and I'll tell you what it's going to be about. But we'll have a quiz next time in the beginning of class.